Hello. So in this new episode, we're going to together discuss the Bayesian persuasion model or the information design problem. Okay. So Bayesian persuasion was first studied by Kamenica and Gentzkow in 2011. So we will focus on their paper to briefly demonstrate the idea of this problem. Okay. So basically, the persuasion problem, it means that the sender or the expert owns some piece of information from the state of nature, but actually it's the receiver that who is making the decision, okay, in this context. So this sender or this expert needs to transmit this sort of the information to this receiver to make their decision, and there's some so this decision made by the receiver will affect the utility of this receiver and the sender. Okay, so the difference from the Bayesian persuasion and between the persuasion and the chip talk game is that in the persuasion game the sender can actually we allow them to have some commitment power for them to commit to a signal, or we call it signal structure or information structure. So this kind of information structure can actually induce a distribution over the postured beliefs of the receiver, so that the problem is sort of more generalized and becomes more interesting compared to the classical chip talk model. So it's kind of an alternative setting, and it's quite different from that. Okay, so now let's get to the basic model of this problem. So there's one sender, okay, and one receiver. So the sender's utility is V, affected by the action of the receiver and the omega, which is the state of nature. So receiver utility is U, depending on A and omega. So V and U, they are not necessarily the same, right? So there might be a misalignment of the interest between them, and that is already embedded in this utility function. So as we mentioned, this A is the action from the action space, and omega is from the state space. Okay. So both the sender and receiver, they have a common prior belief on the omega. Okay. So the omega is then realized according to this prior belief, right? Okay, so there's a very useful assumption in their paper, which is saying that the cardinality of the signal, which is the S is the signal realization. Okay, so later we'll introduce the signal. So the signal realization, it has so its set should be big enough, okay, for some possible action recommendations, and we will mention this later. Okay, so it means that we have to assume that this is no less than the minimum of the cardinality of the action space and the state space. Okay, so that this S is not a small set. Okay, so we assume that it's big enough. Okay, and also this we also need to assume that this S is finite for simplicity. Okay. So what's the key object here? So in this model, we wish to find this sort of the signal, right? And we'll shortly define that. So the key object in the persuasion game is to find this optimal signal, or the or we can call this signal structure or information structure, or Blackwell experiment, or just the data generating process. Okay, so those terms, they refer to the same thing. Signal or signal structure. Information structure. Experiment or Blackwell experiment. Or simply the data generating process. Okay. So those are necessarily the same thing. Okay. So now we can formally define a signal. So a signal, okay, is, we use this pi in our paper. So this pi is a map from the state space to the set of distributions over the signal realizations. Okay. So this simply it specifies a statistical relationship between the truth and data. Okay. Truth and data. Okay, so alternatively, we can define this pi as an element of the data of the product between the set of the state and the signal realization. Okay, so that's another way to define this. But the marginal distribution over the omega should be prior here. Okay. Over the omega is prior. Okay, so we don't need to go too deep into this alternative definition, but we just know that this is also possible. Okay, so the game proceeds as follows. So the timing of the game. Okay, so first, the sender. Okay, sender chooses and commits to a signal pi. Okay, and this pi is actually a public knowledge. Okay, so the receiver can observe this. Receiver observe pi. Then nature starts to move. Okay, so nature first chooses the omega according to the prior. Okay, and also nature chooses the signal realization according to the pi, right? Pi omega. Okay, then the signal is realized, so receiver can observe that. So finally, receiver takes action A. Okay, so that's it. So this A will affect both utilities. So the receiver, they simply act in a Bayesian manner, right? So this action is quite mechanical. Okay, so using the Bayes rule to update their belief, right? The receiver's belief. So mu0 then is updated to mu pi omega given s. Okay, so this is just the Bayes rule. We have this pi here and multiplied by the prior and divided by all the possibilities that this s is sent, right? Given all the possible omega, and use omega prime to denote all the other possible omegas. Okay. Okay, so that's the base rule. And then this receiver simply, okay, chooses an action, okay, A star. So this A star is a function of the mu, okay, given the some signal realization, which is the argmax of the expected utility of the receiver, right? So this omega is realized according to the mu, and this is the expected utility of the receiver. Okay. All right. So given that, so we solve this game backward. So given the behavior of the receiver, right, then we solve the sender's problem, right? So the sender solves the following problem. So maximize over the pi, which is an element of the big pi, okay, and the expectation here, omega is realized according to mu naught, right? And then write the other parts similarly to the receivers, right? So here we have the signal realization is realized according to this signal and the utility function for the senders, okay, given the action for the receivers, okay, and omega for the other part of the utility function. Okay, so this expression here is quite long, right? So we need to simplify that before we can actually start to solve this optimization problem. Okay, so there are some problems with this long expression. So the first thing is that this pi, this set is a very large set. Okay, so the second thing is that the choice of pi, so this influences the sender's payoff by both changing the distribution of the signal realization, right? So that's by the definition. And this also changes the action induced by the S, right? And it's also changing the actions induced by S. Okay, so this becomes quite complicated, right? Then what they in the paper what they provided is a very useful approach to simplify this problem, and this is called the concavification. Okay. Now let's discuss how they're doing this. Okay. So the first important note is that, okay, so when you notice that, so whatever, whichever the pi sender chooses, okay, so the expected payoff for the sender is fully determined by the receiver's posterior belief, okay. So no matter what pi sender chooses, the expected utility of the sender is fully determined by the receiver's posterior. Okay. So it means that if we have a posterior belief as mu, okay, then the center expected utility is, then we can use this v hat, which is a function of mu, okay, and it's simply the expectation with omega is realized according to mu, okay, and the expected utility of the sender given the action of the receiver for the this posterior mu, okay, and omega, okay. So then this is the sender expected utility, right? So a very useful diagram to explain the relationship between the signals and the distributions of the beliefs is as follows. So we know that the signal realization induces the posterior belief, okay. So because that the signal realizes this, so signal realization, of course, it's a realization from the signal, right? And also the posterior belief is also a kind of realization from something, right? Okay, so here we simply define this tau as something which can has the realization of mu, okay, as the posterior. So this tau here is actually the distribution over the posterior belief, okay. So from an ex ante perspective, so this pi is actually inducing this tau, okay. All right, so this little diagram here helps us a lot to better understand the relationship between the pi and tau, right? Okay, so remember that we discussed the Bayes plausible before, right, in the previous episode. So so tau is Bayes plausible, okay, if the expectation of the posterior belief is prior, right? Mu according to tau, right? So the expectation of mu is mu 0, mu naught. So that's the definition of Bayes plausible, okay? So by the law of iterated expectation, every tau induced by the pi is Bayes plausible, right? So by the law of iterated expectation, that's not a good word. Law of iterated expectation, okay. Every tau is then induced by pi is Bayes plausible, okay. Good. Also, for every Bayes plausible tau, okay, on the other hand, so there exists a pi, okay, such that this tau is induced by this pi, okay. So, and we have something interesting for the definition of related to this, okay. So if we let this set of the signal realization is a subset of the action set, so we call this signal is a straightforward signal, okay. straightforward signal. So intuitively, the signal is straightforward. So right. So intuitively, it means that this signal is very clear, and the receiver can just follow this signal to take the action. So in this case, and this signal, this straightforward signal becomes, or it produces the action recommendation for the receiver. Okay, so it produces action recommendation because the set of the signal is smaller than the set of the action, right? So then the receivers, they don't need to think more about the meaning of those signals, and they just follow those signals to take their actions, right? So this is pretty easy for them to take their actions. So this produces the action recommendation, and receivers always follow that recommendation. Okay. Receiver always follows the recommendations. Okay, good. So that's pretty much about the preparation of the main dish. Okay, now let's discuss the main proposition, the proposition 1 in the Kamenica and Gentzkow 2011 paper. Okay, proposition 1 in the paper by Kamenica and Gentzkow 2011. Okay. All right. So essentially, they're saying that the following 3 arguments are equivalent. Followings are equivalent. Okay. So the first, this type of argument is quite similar to the Blackwell theorem, right? This is quite interesting. So the first statement is that there exists a signal with value V star. Okay, all right. So the second thing they say is that there exists a straightforward signal with value V star. Okay, and the third thing is, which is equivalent to both of the above, is that there exists a base plausible distribution of the posterior tau. Okay, so tau is a distribution of posterior. So this tau such that, and this, of course, it has to do something with this V star, right? So it means that the expected utility given this tau is V star, right? For the sender. Okay. So that's the statement of this, the first proposition in the paper. Okay. And now let's prove that. Okay. Proof. So from 2 to 1 and 2 to 3 are just by definition. Okay. And those are immediate. Because if the signal which is straightforward, then it has a value of V star. Then a signal that is straightforward or not straightforward must have this value of V star, right? So this is by definition. And also from 2 to 3, this is also very simple, right? Because that if there exists a signal which is a straightforward signal with value V star, then by the definition of this a straightforward signal which is a action recommendation, then it's plausible then there must exist a base plausible tau, right? So this tau induces actually this tau has the leads to the expectation of the for the sender's utility, which has a value of the V star, right? So those are simply the definitions. Okay, so the remaining parts, first we show that, okay, so those are given by definitions. So the remainings are that we first show that 1 can induce 2, okay? All right, so we assume that 1 is true. It means that we now are given a signal with V star, right? Given signal pi with value V star, okay? So what we are going to do is to actually put all those all those signal realizations together, which signal realizations they can induce one particular action, okay? And so we put all those S's together, okay? Let's see how we are going to do this. So we define a set SA, okay? So the element S here, it makes all those actions, okay, given the posterior belief mu s. So all those little s leads to the same action A, okay? And then if it is so, then we put all those s into this set, SA set, okay? So that's it. That's basically what we're doing here. So now we consider a signal, okay? With the signal realization set is actually the action set, okay? And how about the pi? So the pi prime, this new signal for the pi, which is simply we sum this pi, but over all of those s that is in the set of SA, okay? So we initially define this set SA, then here we add all those pi up over the S, which is an element from the SA, okay? Okay, so what it means? So it means that, in other words, this, okay, let me change the color. So it means that pi prime actually replaces each signal realization with what? With a recommendation, with an action recommendation that the signal realization induced, right? So this action recommendation is induced by this signal realization. So this is the same signal realization. So this sentence from the paper looks quite long and hard to be understood, but this is actually very, very useful to understand the key part of this proof, right? And actually, this is what we're doing here is trying to construct or trying to formally demonstrate the idea of this action recommendation, right? So formally to establish the concept of that. So that the resignalization induced. Okay, let me finish this. Okay, so this refer to the same thing. Okay, very good. So those parts, they are actually they defined the action recommendation, right? This is some comments recommendation. Okay, all right, good. So because that A was an optimal response to each S from the SA set, right? So this A must also be an optimal response to the realization A from the pi prime, right? So because each is true, so together, when we sum them up over all the S's, so the summation together, this has to be true as well, okay? So since A was optimal response to each S, okay, so it must also be an optimal response to the realization A from pi prime, right? Because now here we have this A as the realization, right? Remember that this set of the realization now is actually the set of action. So, okay, and the reason, okay, let me put some comments. So this is because that each is true. So together, when we sum them up together, and this is also true. So this is a very brief explanation, but not very rigorous. Okay, so just an intuition. Okay. All right. So the distribution of the actions conditional on the state under the pi prime is then the same as the one under pi, right? So the distribution of the actions conditional on the state under pi prime is the same as those under pi, okay? So this means that the pi and pi prime, now they induce the same action, the same distribution over the actions, right? Let me comment here. So the intuition is that pi and pi prime, they induce the same distribution over the actions, okay? So because since the pi has the value of v star, right? So then it must be that the pi prime has a value of v star, right? So pi prime has value of v star. Okay, so then that's that completes the proof of this part, right? Then okay, should be black. So finally, there exists a straightforward signal with v star as well, okay? All right, so that completes the proof from 1 to 2, okay? So now we have shown 2 to 1, 1 to 2, and 2 to 3, Okay, so as mentioned in the paper, so next we will show that we are using 3 to prove 1. Okay. So the basic idea here is to mainly construct a pi so that this pi has a value of v star, right? And this pi, this doesn't have to be the straightforward pi. So, but this proof is kind of similar to the previous proof that we did in the splitting lemma, right? And we'll see that shortly. Okay, so now let's start the proof. So for some tau, which is an element of the delta omega, and with this v star. Okay. So let's define a set CV hat, which is simply the graph of the posterior and the center's expected utility. Okay. So that's nothing but this. So mu v hat mu. Okay. And this mu is, of course, an element of the delta omega. Okay, so, and imagine, just for a simple example, right? So imagine that this is in two-dimensional real numbers, and then this is just the coordinate for the mu and v hat mu, right? That's it. That's pretty straightforward, and we can't say straightforward in this video because we have a formal definition of the straightforward. Okay, so this is pretty simple. So the graph, so this is actually the graph or the plot for the mu and its value for the utility function. Okay, so all right. So this mu, okay. Next, we have something very important. So this mu is an element of the delta omega, of course. And so we notice that this delta omega is a subset of reals with a dimension of the cardinality of omega minus 1. Okay. And this is true. I will show this later. And it's a very interesting result. Okay. And also, this is simple, that the v hat of mu, this is a real number. Okay. Real number. Okay. So now let's show this part. So why this is true? Why a set of distribution, it has a dimension of omega, a cardinality of omega minus 1. So why is that? Okay. So let's have some simple example first. Okay. To see some examples first. So if omega only has one element, okay, then this means that we don't have any we don't need to actually find the delta omega, right? Because omega now is deterministic, right? So no need to find delta omega because it's deterministic, because it's for sure, right? It only has one element. So there's no randomness inside. So, but if this set has two elements, okay, so let's take a look at a small picture. Okay, so this is omega, and this is the density. This is the mass. Okay, probability mass. So let's say it has two elements. Okay, it can be this, or it could be something like that. Okay, the left one is higher, so or anything else, right? So it has infinitely many of those combinations, possibilities. But here we notice that we only need one real number to denote this distribution, right? And we can just use this number to denote this distribution. And the other one, we just use 1 minus that, right? And that's it. So this is very interesting and very useful result. Okay, so but if omega has 3 elements, okay, so it might be something like this or like this, okay, anything. So here and it's obvious that we need 2 real numbers to denote this distribution, right? So perhaps we can use those 2, and then for the third one we just use 1 to minus the probability of those 2, right? So that's some very interesting result. So that's intuitively the reason why we're using this superscript as the dimension of the root numbers for the set of distributions over some set, right, omega. So this is the cardinality of omega minus 1. Okay, so that's the reason we are minusing 1 here. Okay, so this is very useful thing to notice. Okay. All right, now let's go back to the proof. So because since tau is base plausible, right? So its expectation of the posterior is the prior. Okay, so in addition, so the V star, it has to be the expectation given tau of the Sanders utility, right? So that's by this definition. So we have something that mu naught and V star is an element of the convex Hall. Okay, so this is just the convex Hall, okay, of this C function, okay, a C set of function. Okay, so intuitive, what does this mean? Let's have another a small picture to try to explain this. Okay, so for example, and actually we will have a lot of those pictures later. Okay, and to demonstrate the idea of the Bayesian persuasion. But here we have something simpler to show the idea here. So this is mu, this is V. Okay, so suppose that this V function, it looks like this. Okay, so a convex Hall formed by this function is just this part, right? So then if our mu naught is somewhere here, let's say, and then this V star is here. So this is actually inside of the convex Hall of the C of V hat. Okay, so that's essentially what we're saying here. So if we have that, then we're able to use the Kamenica theorem. Okay, then by Kamenica theorem, okay, simply it's saying that we can use the number with the points with a numbers of the dimension of that set plus 1 to denote, to actually write that any point in this convex Hall as a convex combination of those points. Okay, and then specifically we'll have those. We will just use this theorem, okay, to show our result. So formally, there exists some posterior belief. Okay, posteriors. Let's say mu s. Okay. Okay, S from 1 up to omega cardinality plus 1. Okay, and there also exists some weights. Of course, we'll construct some linear combinations, right? Convex combinations. So those some weights. Okay. Right. So we use alpha. So alpha S. So S from 1 up to omega plus 1. Okay. So such that, so this is by directly implementing the Carothiodory theorem. Okay. So such that the mu naught V star, this actually equals to the summation for the mu S V hat mu S. Okay. All right. So this S here, this is not the S that we used before. Okay. So this is simply some random S. So S from 1 to coordinative omega plus 1. So where the summation of alpha equals to 1 over the S's, right? Okay, so because this is the weight, and this is just for the convex combination. Okay. And you can check this theorem, Carothiodory theorem, if you are interested in that. Okay. All right. So that's a very useful theorem for us to prove those things like that, like this. So then we can construct this tau star. Okay. So perhaps we should use S star here. Okay. Because this S is not the S that we used before. S star. Okay. All right, so this is more rigorous. Okay, good. So the next thing that we are going to construct this tau. Okay, and this is quite similar to what we did in the proof for the splitting lemma. And then we construct a tau star with an element of delta omega, such that this tau star, given mu S star, is alpha S star. Okay, so this S starts from 1 to up to the cardinality of omega plus 1, right? And this pi is a map from the omega to the Saddle distribution of the signal realizations, and right. So now we have this S, so we don't mix those two up, right? So they also have the same elements here. Okay. And then this construction is similar to the splitting lemma. Okay. Okay, very good. So then what? Then we can show that. So this remember that how we constructed that proof in the splitting lemma, right? So here we actually are doing the same thing here. So this S star given the omega, that is a tau star of mu S star omega given mu naught. Sorry, divided by mu naught for the normalization. And then we can actually, using some simple algebra, to verify that this is a valid signal, right? So how do we do that? And this is also similar to what we did in the splitting lemma's proof. So we just sum over all the s's, s stars, right? So from 1 up to this, okay, and then the denominator is the same. We just sum over the numerators from 1, okay, so tau star, and then we can actually verify that this equals to 1, okay? So this means that this thing here is a valid signal structure, right? Or signal. Okay. So pi is successfully constructed, right? Constructed to be a valid signal that induces tau star, and it has a value of v star, right? Okay, so that's the end of the proof for the proposition 1, and for those 3 equivalent statements. Okay, and later in the next episodes we will formally introduce this problem with some more intuitions and to demonstrate some examples to find the optimal persuasions and the more interesting interpretations of the problem. Okay, that's it.